Hi everyone. I think it's good to start now. Hello everyone, I'm Oktay. Yesterday I talked about how to develop a local planner. Today I'm going to talk about how to develop like a global path planner and what kind of algorithms we can use for that purpose. There are many methods to develop global path planner, but in this talk I will mainly focus on heuristic search-based planners. And again, I compiled this talk based on result of these researchers. If you want to learn more details, you can refer these people's website. So what are we doing here? Like I said earlier, don't think a robot just a mobile robot. You can have different types of robots. Like you may have a helicopter, you may have a humanoid robot, and they may have different configuration. At the end of the day, no matter what you want to do with these robots, you want them to move in the physical world from one position to another position. And usually, you want these robots to obey some constraints. Like there may be some areas that you don't want them to get in. So you have to somehow impose this constraint on your planning algorithm so that it can find a collision-free path. At NASA, we mainly work on platforms that are called Rovers. We have our own challenges. For example, in our setting, like we don't have rods, we don't have lanes, so the terrain is rough. So most of the time, you try to interpret the terrain and you try to understand where you can drive, and you have also very limited perception, like this camera, that it cannot look very far away. And usually you have very limited memory and limited computation power, and you try to do best with your own hardware. So we can state the motion planning problem as follows. So you have a world, and in this world you are given two initial configuration, and there are some places that you don't want to be in. And you give the geometry of this world, and you give the geometry and kinematics and constraints of the robot. Then you give these two initial and goal configurations. And this black box is supposed to compute a collision-free path. And as you may know, there are multiple ways to reach from this point to this one. And usually you associate each path with a cost function. This can be length, or this can be energy. And you want your algorithm to find the path that minimizes cost function. And it's called optimal motion planning problem. But even with that optimality, finding a solution is usually always hard. So, like I said earlier, there may be many algorithms to solve the same problem, and people, they claim their algorithms are better than other ones, and usually they use these metrics. The first one is completeness. Like I said yesterday, completeness means if the problem is solvable, that means there's a solution, you want your algorithm to find it. If it cannot, then you said the algorithm is not complete. And optimality, like I said, there may be multiple ways to solve the same problem. You may reach from here to there in multiple different ways. And if you define a cost function, and you ask if this algorithm returns the optimal solution. And these algorithms exhaustively search in your search space, and they use memory, and they spend time to build this solution. So usually, these two metrics are very important for practical purposes. This space complexity is how much memory it used during the search. The time complexity, how much time it takes to compute this solution. So usually, you want an algorithm to compute something very fast and something that requires very low memory. So in the context of heuristic search algorithms, you usually represent your search space with a graph. Then this graph encodes many solutions. Then you use a graph search algorithm to find the best path in this graph. And usually the graph construction and the search, they are interleaved because the original graph, search graph, may have many nodes and many edges. So it may not be possible to build the graph in advance than search. So usually you interleave the graph construction and the search. So for example, let's say this is our world in 2D, and for some reason we don't want to enter these, so these are marked as no-go zones. So you are given two positions, and you want to find a path between these 2 points. So you first, this is a continuous domain, so first you discretize this world. Then you define these cells. So you throw away those are not feasible. Then you will have these kind of feasible cells. Then you define how these cells are connected to each other, because that defines how you can move between these cells. For example, S1 and S2, they are neighbors, so you say, okay, I can move, if I'm at S1, I can move to S2. And but once you have these transitions, you have the nodes and you have the edges in your graph. Then you use a search algorithm to find the shortest path between these two nodes. So up until this point, the rest is pretty generic. There's a whole literature on graph search algorithms, and they don't care what kind of graph they're working on. So in the context of planning search, you have domain-dependent and domain-independent parts. So the domain-dependent parts, this is where I say, if you work on a humanoid robot, you will have a different graph construction scheme. If you have a quad, or if you have a helicopter, you will have different state. You will have different transitions. So you have to use expert knowledge to build this graph. Then once you have this graph search algorithm is pretty independent of what kind of graph you are searching on. There's a whole literature. Typically, the simple graph search algorithms are like Dijkstra and A-star. And in this talk, I'm going to explain how this algorithm works. The main difference between these two, A-star use what we call as heuristics. And by the way, if you have any questions, feel free to ask. And once your graph search algorithm computes a solution, then you have an execution module, and you try to execute this plan. Usually, it works in a loop. You receive a map, and you get your pose and goal updates, and you try to compute a path, then you try to execute that path. And this keeps iterating until your robot reaches your goal. So just to give an idea, a graph is a mathematical structure. It is defined by the node and edge set. And here we have the nodes are represented by dots, and the transitions are represented by edge. Usually this transition tells you if you can move from between these two states, and also it gives you the cost of moving that state. If these are positioned, this may be the length of the transition. And the tree is a graph, but the thing is, the only difference is each node has just one parent node. So that's the difference between graph and tree. Usually, you represent your search problem as a graph, and you try to find a solution that is encoded as a tree. So for example, once you have this tree, and if you represent your solution like this, if you want to go from here to here, you just follow the parents, and you reach the leaf nodes. Like I said, graph search algorithm is a vast area, and if you want to do path planning, it boils down on this simple principle. It's called principle of optimality, and I will try to prove this, and this will be the only proof in this talk, so it's not that big, that scary. So principle of optimality gives a characterization of your optimal cost-to-go function, and it is stated by Bellman. So this is a long paragraph, but in short, what it says, any sub-arc of an optimal path is optimal. So this is a very simple statement, but it's very profound. So let's say in your motion planning problem, this is your goal node, and you want to find the optimal path from X to goal. So you may have a bunch of intermediate goals, intermediate nodes, and this statement says, if this is the optimal path, any intermediate node you pick, starting from that intermediate node and towards the goal, that sub-arc is also optimal. This makes sense, right? Because if it is not optimal, then you cannot claim optimality for this guy. So let's prove this. So we said, let's assume like this path is optimal. So what does this mean? This means any, like, and this is represented by phi star, pi star. And that means any path in your graph you pick, and j represents the cost function. It says the cost of this pi star is better than the cost of any path you can pick in this graph. So we are going to prove this by contradiction. So let's assume this is not true. Let's assume there is a very interesting node here, and we assume this sub-arc is not optimal. So what this means? This means there exists a path, an alternative path that starts from y, and it reaches the goal. And we claim, and this is like we started contradiction. Let's assume this is not optimal path. That means this yellow path has a better cost, and it is represented like this. The cost of this alternative path is better than the cost of this sub-arc. So now, back to our original path. Starting from x, we have two alternative paths, right? And let's compare the cost of these paths. So let's form this alternative second path. And it starts with this, the first sub-arc, and this yellow sub-arc. So if you write the cost of this new path, you can say it is the cost of this first arc plus the cost of the second arc. So we need to compare this cost value with the cost of p star. So this is the same, and by our assumption, we said the cost of this new arc is better than this one, and that's what our starting statement. And we end up having this inequality. This means that the cost of this alternative path is better than the cost of p star. But before starting this, we said p star is the best optimal path. That means it has the minimum cost. And by using this statement, we reached a contradiction. So this cannot be true. There is no such y such that you can find an alternative path whose cost is less than the cost of the sub-arc as start at y. So this principle of optimality is used in many search algorithms to construct optimal path. So because when you try to develop a path planner, usually you don't want to find a path, optimal path from a given initial goal, given initial node. You want to find a path that from every node in your graph. And this Bellman's equation, it uses a principle of optimality, and it gives you a characterization of optimal cost to go function. So it says, okay, forget about finding the path. It says, let's instead try to find optimal cost to go function. And it says optimal if you give me a cost to go function, it should satisfy this equation in order to be optimal. This simply says if your node is the goal node, the cost to go is 0 because you're at your goal node. And the second statement says the cost to go, optimal cost to go for an intermediate node x can be written as optimal cost to go of the successor nodes, and it is written something like this. So let me explain what this means. So let's say you are at node x, and in your graph, let's say you have some successor nodes. And this is your goal. And these nodes are connected with some optimal path, but you don't know, let's say. So if you know optimal cost to go for these guys, these successor nodes, And also, let's say you don't know how you can reach from S1 to S goal, but let's say magically you are given the optimal cost to go value. Then if you know the optimal cost to go for all successor nodes, then if you know the transition cost from X to S1, and if you think these are two different positions, this may be the length of the path, and let's say these are represented by this C. So now the question is, how can we find optimal cost to go for this vertex, this node? Well, you know, if you are at S1, there's a path that will take you from here to here, but you don't know explicitly. But you say, I know the cost. So you can say, at X, I can try to follow S1, and I know the cost to go from here now onwards, and I know the transition cost. So you can say, I have this option. The first option is, let's say, via S1. You can say, I have this a candidate solution, right? And you have all these alternatives, right? So you want to find the optimal path. Then you have to compare the total cost of these alternative paths. Then you find the minimum, and you say, OK, the optimal cost to go of Jx can be written as so that's what it says. It's a characterization of optimal cost to go function. So why optimal cost to go function is important? Because once you compute this optimal cost to go value for every node, and maybe you may have some intermediate nodes here, right? So once you find this optimal cost to go function, then you implicitly encode all optimal path from any node. Yes?
That will just be like the distance between the parent node and the other node. And
yes.
Then the cross function at the other node would just be the sum of the attractive and repulsive forces?
No. Here we don't have any repulsive, and like here I assume like you may have many nodes, and this is very abstract. There is no repulsive force. I'm just saying I give you a bunch of nodes, and I define the cost between transition between these nodes. And this cost may be, like if you do path planning, it may be path length. But usually, like in engineering problems, you want to you may want to minimize the energy. Like this is just some quantities you want to minimize. It may be time, it may be path length. So think this in an abstract way. So you have a bunch of nodes. I give you cost function. This may be meaningless as well. So this principle of optimality just gives a characterization of how to find optimal cost to go function. And I'm saying if you find this one, then you implicitly compute all the paths. Because if you are at X and you want to find the path, you can say, I'm going to solve the minimization, and I will find the best successor. And for example, let's say if S3 is the minimum of these alternatives, then you can say, if I'm at X, I'm going to move in this direction. And you can repeat the same procedure for S3. You can say, if I'm at S3, you have multiple alternatives. And you can say, oh, this node is the minimizer, so you will follow this direction. So, and you will keep doing this until you reach your goal node. And that's why this path planning, like this path planning problem is, it boils down to compute this optimal cost to go function. So So once you have these, you not only find the optimal cost, the optimal path for your initial vertex, but every vertex in your graph. But the computation of this thing, you use some algorithms to compute this optimal cost to go function. And one of the algorithms is called Dijkstra algorithm. This is one of the simple algorithms you can find in this. And this is a little bit complicated algorithm, so I'm not going to explain what are these. But I can say, so you want to compute J star, and this algorithm uses two estimates of J star, J and J bar. And J bar is defined in a similar way for J star. But here, the only difference is it uses the estimate J instead of J star, because we are trying to compute J star. So we have we have J, for every node, we have J, J bar, and we assume J bar satisfies this condition. And we have something called a key, and this key is the value of J bar. And we use a priority queue to order these vertices. And we always use, we do some updates, and we always pick the nodes that has the minimum key value. So in this very simple problem, let's try to understand how Dijkstra algorithm work. So I have a queue, and I order this queue based on their key values. And I'm at this green cell, and I'd like to reach this red cell. And these black cells are you don't want to reach. This is not a feasible motion. And you initially start with this configuration. The first value is J value. The second value is J bar value. And at the goal, your J bar value is 0. And what you do, the algorithm starts by putting this goal vertex in the queue. And its key value is J bar, and J bar is 0 for this goal vertex. You can think of J bar as an estimate of optimal cost to go. So what the algorithm does, at every step, it checks the queue, and it picks the top vertex. And here we have only one, so it picks this guy. And it performs one operation, we call this operation the expansion of a node. So when I say an expansion, it means it takes this J bar value and assign its J value. It's like you make assignment from right to the left. Then you check your neighbor vertices, and you update their J bar value. So J bar value was minimization over alternatives. Like for example, if you are here, you have transition cost one step, right? And the cost to go is like the J bar value is 0. So this is your J bar value for this node is 1, and this is 1.41, and this is 1. So once you update their J bar value, you have 3 nodes, and you put them in your priority queue. And this is just one expansion step. And this algorithm keeps doing that for many iterations. Now, in the next step, it will again check the queue, and it will pop the vertex on the top of the queue. And here is this one. And it expands this vertex. So what it does, it takes J bar value and assigns it to J value. And it updates J bar value of neighbor vertices. Then it puts them in the queue. So you can think of this orange color as a frontier. And simply the algorithm keep expanding all these nodes, and it will push this frontier all the way until it hits this our initial vertex. So if you repeat this algorithm, as you can see, it will keep expanding. And do you guys see a pattern here? So it's like it expands things in a radial fashion. And it's like it pushes frontiers in a radial way. And the other thing is, check the value of key value of the top vertex at every iteration. So what happens What happens with this value? It's always increasing, right? It never decreases. Like initially, we start with very small values, but when you keep expanding, it keeps increasing. So as you can see, the algorithm is a little bit slow because it expands too many vertices. And so you can think of, like as you can see, when you expand a vertex, you always record the successor vertex that yields the minimum cost to go value, and you assign these back pointers. And you can think of this kind of a force field. Like if you are here, it will tell you you have to go this cell. If you are here, it will tell you you have to follow this cell. So you keep doing this until your vertex of interest is in the priority queue. So at some point, this guy enters a priority queue, and you keep expanding this. You keep expanding vertices, and the algorithm stops when your initial vertex is popped from the queue and you expand it. Once your initial vertex is expanded, then you can reconstruct your optimal path, and by just following these arrows. And the algorithm terminates. And it will tell you, OK, optimal path from this guy to this one is represented by these red arrows. So this is the basic idea of like a graph search algorithm. So people, they propose different algorithms. These algorithms differ in the way they expand these vertices, in the way they operate on this priority queue. And do you guys think if there's a way to improve this search, like what can be improved here? Like we expanded so many vertices. Yeah?
Maybe like only like don't do the ones that are getting like too big. So like if you already split a shorter path, only go into that. So like you obviously know that like you shouldn't go down because like, it's getting like, a lot bigger.
But like you see the big picture here, but your algorithm just see these key values and nodes. It doesn't see, like when you can see, you somehow know the optimal path is here, and I should not going this way. So how can you give this hint to the path planner? Yes.
Maybe you follow nodes that get closer to the goal.
That's true. Yes.
Perhaps start at nodes that are actually like, surrounding your current nodes, like instead of starting from like up here and then like working your way through the.
Yeah, that's like you can say you can have two algorithms. One will start from here, the other one will start here, and in the middle they will merge. So yeah, these are good ideas. Like and like the way the people improve these algorithms, they try to minimize the number of expanded vertices, because these nodes are stored in the memory, and if you expand more vertices, that means you have to use more memory. So more or less, like you guys gave good hints. Like people, they call it heuristic. Heuristic is kind of a little bit hint to the algorithm to where to explore. So for example, in A-star algorithm, it's a heuristic-based search algorithm. It's like similar to Dijkstra. But it introduced a new component here, and it's called heuristic. So heuristic is a function. You give two nodes. It gives you underestimate of true cost. For example, if you want to move from here to here, and if there are obstacles here, your heuristic will be the straight line distance, right? Because you know there is no shortest path shorter path than a straight line distances. And we know that if there are some obstacles in the environment, the alternative path will be a little bit different, and its cost will be very large and heuristic cost value. So this is the function that you want to design for a specific problem, and this can significantly improve your search performance. So in A-star algorithm, once you have this algorithm, this heuristic function for your application, you update your key values just J bar plus this heuristic value. And this is how the algorithm works. Again, we have the same setup, and we can compute the heuristic function. So simply, the heuristic function is the cost from here to, like from any given node to your initial vertex. And it is a straight line distance. Like you can compute this function in advance. For example, if you are here, the cost is 1. If you are here, the cost is 1. If you are here, this diagonal, the cost is 1.41. If you are here, the cost is something like this, like always straight. And it doesn't consider the obstacle. Like it's optimistic value. Yes?
is like still how you get like those point values. So like for example, in row 2, column 3 was 3.16. Row 2, column 3. So it goes from like 3 to 3.16. Yet on top it goes from 4 to 4.12.
So it's like a straight line. That you know the coordinate of this is 2 and 2, right?
Yeah.
And the coordinate of this 5, 2. So what is the straight line distance? It's 3. For this one, it's the straight line like this. Like it's the square of this length plus square of this length, and you take the square root of that. It's like it's a hypotenuse. It's like a so you have this guy. So this is the length of, what is this? And this one, 5, 2. And this is 2 and 2. So we know this is 3 length, right? And we know this is 1. So the straight line distance is and that's the value. So that's how you compute. Like I said, this heuristic is an underestimate of the true cost. These functions should be very easy to compute for your algorithm because you have to you will use this value for every cell. So you have this heuristic function. That means you can query during your search. Then you start your search again. Now in the queue, previously we had 0, but now we don't have 0. We have 7.21. And for the goal node, we know the key value is and this is the key value of X goal. And for the goal node, we know this is 0, right? So the key value is just the heuristic. So that's why it different from Dijkstra algorithm. It starts from 7.21 because that's the straight line distance between these two nodes. And again, if you follow this will be the direction of the search. So as you can see, it is very aggressive. It tries to expand vertices towards the initial vertex. So here, as you can see, it doesn't go all the way down. And this is how you encode, this is how you guide your search algorithm. So if you are familiar with your engineering problem, and if you come up with these heuristic functions, you can somehow encode, and you can provide that heuristic function to your graph search algorithm. And as you can see, it already reached the initial vertex, and it didn't go all the way down. So you can think of this heuristics prevents your graph to explore your search, like search space that are not related to your path. And you expanded fewer vertices, yet you compute the optimal path for this guy. So this is these are the two algorithms, Dijkstra and the algorithm that uses heuristic, and it's called A*, and this is how they work. So this is the effect of the heuristic function. And if you don't have a heuristic function, and if you use Dijkstra algorithm, and if you want to reach from initial to the goal, you can think of this will be the set of vertices you will explore. If you use heuristics, then it will significantly reduce the explore space, and you will explore. You will store fewer number of vertices in your memory, and it will compute a solution much faster. So for a realistic problem, like I said, you have to define your graph, and for your graph, you have to first define your node set, and then you have to define a transition. For example, if you are trying to do path planning for a self-driving car, so you can think of your node may include 3 values, x, y, and heading. Then you have to define the transitions. And you can say, from this heading, I may have some motion primitives, and you can define these motion primitives, and you can define the feasible transitions. And you can define this for every node in your cell, then you will have your search graph. Once you build your search graph by using these primitives, and you can use some search algorithm, like some version of A star, and this is called anytime version of A star. So these are very engineered algorithms for the specific problems, but they use mainly the same, the same principle. So it's like a variation of Dijkstra or A star algorithm. So these are the basic algorithms. So these are the algorithms out there. So how do we leverage this algorithm in the context of space exploration? Well, we have some robotic platforms at NASA, and we use these Rover platforms to explore planets. And the main challenge in our work is like you try to drive these rovers on a very rough terrain. Like you may see very high slope, and you may see craters. So you don't want your rover to fall down this crater, otherwise it will be very sad. Then you see lots of mountains. And these terrains are hard to drive, and so you have to be very careful where to drive, and you have to be very careful how to command your wheels. Otherwise, you may end up, you may get stuck some areas. For example, sometimes the rover tries to traverse on very soft terrain, and sometimes it gets stuck. And it makes it harder to drive on these terrains. For example, in this case, it was very hard, but at the end of the day, scientists, they explored some terrain that are not visible before reaching there, so it may not be always the bad. And you may have rocks like this, and you want to avoid, you don't want your rover to collide with these rocks. And sometimes you hit a terrain that you haven't seen in the world, so this may be a new challenge as well. And don't think like these rovers, they drive very, very far distances. Like these are very memory and computation-wise limited platforms, and usually you drive very short distances. For example, this is the path of Sojourner. It just drove like 100 meters in 3-4 months. And this is the drive path for Spirit rover. It landed here, and it drove all the way to Dawn, and it took 6 years. And if you check, this is just a couple of miles. So usually, you can say why, if this is the place you want to explore, why don't you land here? Well, landing is a very challenging problem, and usually when you say I'm gonna land here, usually there is so much uncertainty, and you have an ellipse. You can say I can land any point in this ellipse, and you try to fit that uncertainty ellipse in a place where it is safe. So usually, these regions of scientists, they want to land, they want to traverse near craters, rocky environments, but these environments are not safe to land. An engineering team, they say, okay, we should land far away. You land very far away, then you try to drive from that landing site to the region of interest, and it takes some time. And this is another drive path for opportunity, and it's kind of like in 12 years, it drove from here to airport, so it's not that much distance. The main reason is the environment is very challenging, and the communication, there is so much communication delay, and space applications are applications where you have risk, so much risk, so you cannot afford to lose a rover. So you try to drive very short distances, and you try to pick the path that is safest. And this is the recent rover Curiosity, and it drove 13 kilometers in 4 years. As you can see, as we develop new rovers, we try to improve the driving distance in shorter time. So these are the robotic technologies that we use on the rovers. Like these the autonomous navigation software is called AutoNav. So usually, if the terrain is not so rough and it is safe, then people they like to use AutoNav. They want rover to decide where to drive, how to drive. So this is kind of the configuration in the current Mars rover. There are so many cameras, but for navigation, we use a couple of them. Like these are the top 4 cameras that we use to detect obstacles, and they are called nav cams. And we have some cameras that are close to the bottom of the rover, and this checks obstacle close to wheels, and these are called hazard cams. So this autonomous navigation software takes images from these cameras and process and try to find the best possible path. And it's another picture of HazCam. So these cameras, they check the ground and they try to see if there's a hole or there's any dangerous thing nearby the wheels. Because wheels are very important. Even if you lose one of them, then you cannot move. So that's why they try. And most of the time, the terrain on the Mars is very hard, and they try not to drive over rock because it may wear out the wheels. And this is the HazCams. They just check nearby, and we usually use this platform to rotate the head so the rover can look around and take pictures. So we have this autonomous navigation software, but it has different modes, and human operator on the ground can define which mode to drive. So this is how the rover drives. It drives a little bit. It uses cam. It takes a picture around, and it drives a little bit further, and it stops and it checks again, and it turns the wheel and it drives. And just this rotating the head and taking pictures and process, it takes just 25 seconds. Just let you know. So this is a little bit accelerated. Usually this is called visual odometry, because the terrain is very, sometimes it's soft, sometimes it's sandy. You command something, an arc, the rover drives, but sometimes it doesn't go where it is supposed to go. So you have to constantly check. You have to take these pictures and check if you achieve where you want to drive. Like I said, we have different modes of navigation. Like it's just not an algorithm. You just give the goal and it drives. So you have different modes of operation. Like you say, I'm going to drive, and at this time I'm going to run the visual odometry, and I'm going to use an algorithm called sleep check. Sleep check algorithm detects how it deviates from the terrain. Then these are the HazCam pictures. Like after each drive, the rover takes these pictures and compare these pictures with the previous frames. And by processing these frames, it can tell how much it exactly moved. And this tells if the rover slipped or not. And this is very necessary if you want to drive very long distances. And right now, the maximum distance that they can traverse in one single Martian day is kind of 150 and 200 meters. But usually, you use this software if you are very comfortable with the terrain, and if you say, okay, the terrain is kind of not so dangerous, the algorithm can figure out where to drive. But usually, if it's a very dangerous area, we have a team of people, they are called rover planners. They take all the pictures and they do all the computation manually. They give the drive commands to rover and they upload to Mars. And then rovers execute these commands. And like I said, the main reason we need VO is because unpredictable slip. Sometimes you go to some terrain and you say, okay, drive 1 meter, but it drove 1 inch because it got stuck in the sand and it's just spinning and spinning. If you don't do this VO check, I mean, you may have a path, but you will not know how much you drive in reality. So this VO is very important for robust navigation, I would say. These are the challenges that are different from driving on Earth, because here everything is structured. You have roads, you have lanes. If something happens, you can call AAA and you can get some help. But on Mars, if something happens, you have to make a mission and send another thing to help, and it's very expensive. So, like I said, these cameras are used to take pictures, then it is somehow converted to a 2D map where you can drive. And sometimes, even if there is no hazard, the operator may say, I don't want to drive between these areas, or these areas are marked as no-go. And you use this graph search algorithm to find the best path from a given position of the rover. So these are some pictures from drives of the rover, and this is the path it takes. Again, it drives a little bit and takes some pictures and drive and until it finished. Sometimes it cannot proceed and it tells the operator I cannot go. Then for those challenging cases, rover planners, they analyze the images and they try to help the rover to guide the rover from where it is. So here, this is a one path. There's a little bit of rock here, and it tries to avoid. These are, like I said, these are not very fast systems. Like people, I think nowadays they see so many self-driving car pictures, videos, and they think the rover drives like very fast, but that's not the reality. Like I said, on a very flat terrain and on a very successful day, if they drive 150 meters in one day, they say, oh, this is a very productive day. And that's why it takes so much time to go to explore interesting sites. So again, this is another drive path of Spirit rover. And after each drive, like they get all the telemetry data and they analyze why the rover took this path, what caused the rover to take this route instead of going all the way. Because you have a software and you upload there and you assume the software is correct, but you may have a bug in your software as well. So they constantly check the actions that were taken by the rover and try to see if it makes sense or not. So this is like a continuous development process. And these are the, on the rover, they use a variant of A star. It's called Dijkstra. You can think of it as a dynamic A star. So this Dijkstra algorithm, it works on environments with partial information. In the example I gave, I said you have this 2D grid map and you know the full environment. But most of the time, you have very little bit information about where the rover are, and you don't have that much information further away. So this algorithm helps to navigate on map that you have a little bit of information and you try to explore the rest. But again, these algorithms, they use the same simple principle, like principle of optimality. They differ in the way they are implemented. They differ in the way they use the heuristic function. But in terms of search, they have the same principle, I would say. So this is the Dijkstra algorithm as a Dijkstra implemented as global planner on the opportunity rover. So this red area is dangerous. We don't want the rover to go here. This is if you have to go, and this green area is a safe area. And this is how like how the rover planned this path during that sol. So after each day, we get all this telemetry data and we replay on simulation software, try to see if these decisions make sense. If there's something wrong, then we try to fix them. So these are the odometry history of the Curiosity rover. So these colors are, like we have a navigation software, but it has some parameters, and these colors are different modes of operations. And this x-axis is the sol, which is the Martian day, and this is like how much you drive during that day. Like I said, this is 140 meter, and most of the time, like the average is much like 20 meter. Like you drove 20 meter a day, so think of it's not so fast. So this is another plot that is interesting. So this directed, you can think of this directed drive is where a rover planner, a human, gives commands to rover, and the rest is kind of some form of autonomous navigation. So initially, people, they were very reluctant to use autonomous navigation software. Space is very, like the risks are so high, and people, they are so cautious. So in the beginning, you can see the majority of drives are directed drives. That means humans are computing the path actions, and it tells they tell the rover to drive. But as they gain more expertise about Martian terrain, then they start using this autonomous navigation software. So this is the I think 1300 sol, and you can see almost like 80% of drives, they use some form of autonomous navigation. So it's good to learn these robotic technologies because they are used heavily in space, I would say. So, and last thing, do you guys have any cell phone? Anyone has a cell phone? So what is your spec? Like what is the processor, what is the memory? You know? Does anyone know which phone he uses? And
it's like the Snapchat 810, and then it has like three gigs.
okay. So these are the flight rover specs we have. So on the MSL we have 0.5 gigs, and we don't have a gigahertz processor. It's megahertz, and it's very slow. And this is the first rover on Mars, and it was 2 megahertz, and this was the total memory. And this is the memory the whole autonomous navigation, whole flight software use. And usually you have a chunk of it for path planning. So every bit counts, every cycle counts. The reason why we have these slow things because the Martian operating environment is very challenging. Like the temperature difference is so high between day and night. And second, it is subject to so much radiation, and they tried to increase the clock speed, but I think on Martian environment, if you try to run it faster, it will burn. So that's why they have very slow processors, slow memory, and but for new rover, for Mars 2020, they are planning to use FPGA, so that will be kind of a good speed up. So this is my end of my talk. So I just want to say one more thing. So this is a nice picture. It's a nice proverb. If you study history in ancient Rome, there's a proverb called "All roads lead to Rome." That means in politics, no matter what you do, everything will be around Rome. And it also means, if you check the Roman architecture, all roads are connected to Rome. If you want to reach to Rome, no matter which path you take, you will end up to Rome. So that's kind of the meaning. I studied motion planning algorithms for kind of a decade, I think. I would say the robotics people, they study motion planning, control people, they study motion planning, AI people, they study motion planning. If you follow all these algorithms and try to understand why they work, you will end up these two guys. This is Richard Bellman, and he's a mathematician, and he is the inventor of a technique called dynamic programming. And there's also a nice article about why he chose this name, dynamic programming. I suggest you to read that. And the second guy is Pontryagin. He's a blind person, but he developed so much theory in math. These techniques are usually using control. So I studied control and computer science. So I realized people in CS, they usually know this guy. People in control, they usually know this guy. So it's better to know both, I would say, for your career. And thank you so much. If you have any question, I can answer. Yes?
Like, I'm a little bit confused on why you do that calculation over A star. Because wouldn't A star always be the shortest path if you can hear it?
No, A-star algorithm is optimal, and it's called efficient. That means it expands, like it tries to reduce the number of vertices to be expanded without sacrificing optimality. So there are some proofs. The only condition is your heuristic function So I said it used this heuristic function, right? And it's like vertices from some real value. And this heuristic function is called admissible. So this is the true cost to go for this vertex. And this heuristic function should be always underestimate of this value. There are some proofs. If you have this heuristic function, and if it's at this property, then it is proven that A star is optimal. So you can think of, in Dijkstra case, it is the same like A star, but its heuristic function is 0 for every vertex. That means like for every vertex, you don't have any information. So it's the Dijkstra. And if you have a little bit heuristic, like a little bit guidance, then you can give that information to the search, then it becomes A star. But if for some vertices, if you have these, then you cannot guarantee optimality. Like the algorithm may terminate with a suboptimal path. Yeah. Yes? Yeah.
I was wondering, how can you determine, what are the factors that you take into account to determine the amount of vertices, like how fine the grid is? That must affect, how well the algorithms work, but also
Yeah, that's a good question. Like, I would say that's very important step of formalizing your problem, because we live in a continuous world. Like this, when you say I'm going to do path planning in 2D, it's a continuous world, but your algorithm works on discrete structure. So you have to discretize this continuous world and convert to a discrete graph. So if you don't do discretization very well, like if you use very coarse resolution, you may get very fast algorithm. It may find a path very fast, but the path will be very, let's say, you are here, you want to go here. If you use very coarse grids, you may have motions like this, but we know that optimal path is something like this. Like you have to find, like you have to use a better resolution. So there's a trade-off between solution quality and like the quality of solution and how much time it takes to compute a solution. And it's kind of a, say, engineering design parameter. You can start with a coarse solution, coarse resolution. You can test your algorithm. You will check the result. If it's not good, then you will improve. You will improve your resolution. But if you use very like tiny, small resolution, then it will take minutes for your algorithm to compute. So you have to keep this balance in a nice way. And there is no generic rules. Like it is very application dependent, and it's always a requirement of your for your boss. Like you will propose some solution. If your boss happy, then you can develop that software and deliver. So it's kind of application dependent and task definition dependent, I would say. I mean, for example, for these new rovers, they say they say we are gonna give you 2 megabytes for your path planner, and we want your algorithm never use 2 megabytes. So you have to use all these tricks to make sure you can have a path planner that can work on this setting, and its memory usage is not 2 megabyte. It may not find the optimal solution, but it will find a solution good enough for your hardware constraints, I would say. Yes? I would say historically, the Dijkstra algorithm proposed first, and people learn how to do search. Then they say, how can we speed up? And they came up with these heuristics ideas, I would say. Yeah. Okay, thank you so much.